Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 47, Organic Chemistry 1. Today we will continue on chapter 11, Ethers, Epoxides, Thiols and Sulfides. We will cover thiols and sulfides and close up the chapter by discussing synthesis strategies involving epoxides. Nomenclature of thiols. Sulfur is directly below oxygen in the periodic table. Oxygen, down there is sulfur, and therefore many oxygen-containing compounds have sulfur analogues. Sulfur analogues of alcohols with an SH instead of OH group are called thiols. Here we have pentane 1-ol with OH. Having SH instead of OH, we call it pentane 1-thiol, and as you can see, we kept E on. SH group is named as a substituent called mercapto. So if we have OH more senior than SH, so the compound suffix will be ol. So this compound 1, 2, 3, 4, 5 will be pentane 1-ol because we decided that we will call it ol. So on carbon number 5, this is 1, 2, 3, 4, here is 5, will be mercapto. The SH will call mercapto group. Provide the IUPAC name for the following compounds. These compounds, here is S, 1, 2, 3, 4, 5. S will be senior, so the suffix will be thiol. So it is bent for in 1-thiol. Here is 1 and here is number 4. What about this one? Long chain, this one, containing the SH, so it's thiol. 1, 2, 3, 4, 5, 6, 7, so it's heptane 3, 1, 2, 3, 4, 5, 6, 7. On 5 we will find chloro. On 4 cyclopropyl. So it is 5 chloro, 4 cyclopropyl, heptane 3 thiol. In this compound we have two functionality. Aldehyde, which is more senior, so this will be number 1, and here the SH we call it mercapto, and we have on 1, 2, 3, 4, so it is butanal for the aldehyde and 2 mercapto for the SH. So the compound called 2-mercapto butanol. Preparation of thiols. From alkyl halide, thiols can be prepared by SN2 reaction between sodium hydrosulfide and suitable alkyl halide. So if you have 1 bromobutane, Br is good leaving group, SH is a good nucleophile, so via SN2 mechanism we'll get butane 1-thiol. Here we have chiral molecule, chiral center, S2-bromobutane. This is good nucleophile. You mentioned is SN2 mechanism, right? then we are expecting to come from the back side with inversion in configuration, yes, and we got R-butane to thiol as a product. One problem with this reaction is that the thiol product can undergo a second SN2 reaction with an additional alkyl halide to produce a sulfide side product. This problem can be solved by using thiourea as a nucleophile instead. The reaction first produces an alkyl isothiourea salt and an intermediate. This salt is then hydrolyzed by the reaction with aqueous base. Thiourea will act with the sulfur lomber in an S2 mechanism and kick the Br out to form the alkyl thiouronium bromide salt. Then with aqueous base, sodium hydroxide will hydrolyze by attacking on this carbon. 2 electrons will go to the sulfur and neutralizes it to form this species. Another base will abstract this hydrogen, leaving 2 electrons to form the double bond and goes to sulfur the 2 electrons to form the thiol and urea. Thiols easily undergo oxidation to produce disulfide. Thiol with bromine, sodium hydroxide led to the formation to disulfide. If you would like disulfide to go back to thiol, we reduce that reduction with zinc HCl as an example. What about the mechanism for the oxidation? Ethane thiol in the presence of bromine sodium hydroxide. Sodium hydroxide will take the initiatives. First step, proton transfer, deprotonation of the thiol to form thiolate. The thiolate sulfur negative charge attack on Br, partially positive, kicking Br out to form ethyl hypobromo thioate intermediate, which will be attacked by S thiolate S minus to kick the Br out and to form SS bond disulfide, or what we call it 1,2 diethyl disulfane. Nomenclature of sulfides. The sulfur analog of ether called sulfite. So if you call this ether, so that will be thioether or sulfide. Before we have to alkyl, and then we call ether as one of the type of nomenclature. In this case will be ethyl, butyl, B comes first, so it's butyl ethyl sulfide. In this case, this will be a side chain, so we'll call the side chain alkyl thio. Here is 1, 2, 3, so that's cyclopentene. On carbon number 1 we have methyl. On carbon 3 we have methyl thio, 3-methyl thio. Preparation of sulfide. Thiol in the presence of sodium hydroxide will lead to the formation of thiolate. Thiolate will react with alkyl halide to form the sulfide. Here we have 1, 2, 3, so that's propyl, and here 1, 2, 3, 4, so butyl. So this one will be butyl propyl sulfide. Since sulfides are structurally similar to ethers, we might expect sulfide to be as unreactive as ethers, but this is not the case. Sulfide undergoes several important reactions. Sulfides will attack alkyl halide in an SN2 reaction to form sulfonium salt, like dimethyl sulfide react with methyl iodide to form trimethyl sulfonium iodide. This one is a good methylating agent. Sulfide also undergo oxidation to give sulfoxide and then sulfone. Sulfide, oxidation to give sulfide with S double bond oxygen, further oxidized to form sulfone. The treatment of sulfide with hydrogen peroxide or peroxy acid will lead to the sulfone. If we use periodic or periodate, we can get the sulfoxide, which then can be further oxidized to sulfone using hydrogen peroxide or peroxides in general. Aromatic and aliphatic sulfides are oxidized to sulfoxide and sulfone in high yield using 30% hydrogen peroxide under organic solvent and halogen-free condition. Dialkyl, alkyl, and real sulfides are cleanly oxidized to sulfoxides using aqueous hydrogen peroxide without catalyst. So the lone pair of the sulfur of sulfide will attack on the oxygen of peroxide, cleave the OO bond to form alkoxide and sulfur with positively charged. So the alkoxide will go back and abstract proton, leaving these two electrons to form a double bond and the sulfoxide. These two electrons will attack further on the peroxide, cleave again the OO bond to form the same type of species, S with positive charge, OH. Alkoxide will go back and abstract the proton, leaving these two electrons to form S double bond oxygen and furnish sulfone. Potassium hydrogen persulfate, common name Oxone, in aqueous methanol was found to be convenient, inexpensive, and chemoselective reagent for the oxidation of sulfides to sulfone and sulfoxide. The lone pair of sulfur can attack on the O atom of the oxone, and these two electrons will move to form oxygen double bond sulfur, and this hydrogen will transfer to hydrogen, and the oxygen bond established by forming double bond oxygen. Again, this lone pair will do the same, attack on the oxygen, cleave OO bond and form S double bond O, Double bond O here with sulfur will be single bond and catch OH bond. And once again here we will have a second S double bond O, sulfone. So the first step is to form sulfoxide, further oxidation to sulfone. Organic sulfides can be oxidized with periodate to sulfoxides under mild condition. So if you have methyl phenyl sulfide with sodium periodate will give methyl phenyl sulfoxide. Stop. On the other hand, oxidizing the same molecule with hydrogen peroxide will further oxidize to give methyl phenyl sulfone. There are two different ways of making 2-ethoxyoctane from octane to ol using the Williamson ether synthesis. When pure negative octane 2-ol, LEVO, rotatory octane 2-ol, of a specific rotation of -8.24 is treated with sodium metal and then ethyl iodide, the product is 2-ethoxyoctane with a specific rotation of -15.6. When pure negative octane 2-ol is treated with tosyl chloride and pyridine and then sodium ethoxide, the product is also 2-ethoxyoctane. Predict the rotation of the 2-ethoxyoctane made using tosylation sodium ethoxide procedure and propose a detailed mechanism to support your prediction. Okay, we have octane 2-ol with chiral center. So assume that we have the S is a levorotatory 1, reacting this alcohol with sodium will lead to the formation of the alkoxide. O- will attack on the CH2 of the acyl iodide, ejecting the iodide and form the S2-ethoxyoctane with specific rotation given -15.6. Nothing happened to this chiral center, no reaction occurred on this carbon. On the other hand, reacting S-octane 2-ol with tosyl chloride pyridine, transfer this OH to O-tosyl, which is good leaving group, will be attacked by the esoxide by SN2 mechanism with inversion. So the reaction now occurred on this carbon, on the chiral carbon, with inversion. So we got the 2-ethoxyoctane, but we get the enantiomer of it, of the first one. So if this one specific rotation -15.6, we immediately expect that this will be plus 15.6 because that's the enantiomer. A new graduate student was studying the insecticidal properties of a series of polycyclic epoxides. He epoxidized alkene A using two different methods. First, he used metachloroperoxybenzoic acid, which gave an excellent yield of an epoxide he labeled B. Then he treated alkene A with bromine water to form bromohydrin, followed by 2,6-dimethylpyridine to form an epoxide in fair yield. To his surprise, the second method produced epoxide C with different physical and chemical properties from the first. In particular, C reacts with stronger nucleophile much faster than B. Propose structures for B and C, and propose mechanism to show why different products are formed. Explain why C reacts so much faster with stronger nucleophile. Here is the alkene A with metachloroperoxybenzoic acid give epoxide B, with bromine water followed by 2,6-dimethylpyridine provides C. B and C are different. C is much more faster to react with strong nucleophiles. The only function group we have here is the alkene, a double bond. Usually, alkene with sp2 carbons, alkenes are planar with two faces mirror image to one another. We call them enantiotopic faces. However, in our case, with the presence of bridge over one of these faces, make these two faces distereotopic. One will be sterically hindered face, where the bridge is, and the other one will be less sterically hindered. I put these faces in the 3D. See, this is the upper face. And this is the bottom face. But I just flip it. As you can see, this face is not sterically hindered at that one. So the peroxy acid will be attacked from the bottom face to form this epoxide. Agree? Then we go next. When we add bromine water, then we agree now that the bottom face will be the reactive one. So the bromonium bridged, this one will form, not the one from the up, right? Then the water molecule may attack on this carbon or that carbon to form these bromohydrin, right? When we react them with base 2,6-dimethylpyridine, the O-, this base will abstract hydrogen, these hydrogens, to form O-, act as a nucleophile, will come from the backside of the bromine, ejecting Br, the same as here. So from this mechanism, the epoxide will be this one from up. Epoxide B and epoxide C are diastereomers and will have different chemical and physical properties. Epoxide C will react indeed with strong nucleophile much faster because of the less hindered face attacked. Okay, this face will be less hindered. That's why C will be more reactive. Show how you would convert 3-bromo-cyclohexanol to the following diol. You may use additional reagents you need. Well, this is the target molecule. This part of the molecule is the same as this one. This is the new. So we cut in here. We can get this molecule from the reaction of this anion with this ketone. Can we do that? Can we create anion in the presence of OH in the some molecule or others in the media anyway? No, we can't. So this OH should be protected first. So we'll start with 3-bromocyclohexanol reacted with silyl chloride, trialkyl or triisopropyl silyl chloride in pyridine, form O-silyl bond, protect the OH. Okay. Then we react that with magnesium in ether. We form alkyl magnesium bromide. We react this with ethyl methyl ketone or 2-butanone. We form this salt. Treat that with water. O magnesium bromide will be OH. Then react this alcohol with tetrabutyl ammonium fluoride. We deprotect the OH once again, and we have free OH. I hope that you have enjoyed Organic Chemistry 1. We are done with that course. Best wishes, and looking forward to see you in Organic Chemistry 2.